because it is about that time. So, hello everyone. Welcome back. We're on day number two, and I've actually already tweaked the schedule a little bit based on how Monday's class goes. I wasn't quite expecting to have to plan that, but the reason I did that is for four reasons. One, I mean, I think these classes are long, like we talked about. And, having me stand up here yakking for 2.5 hours is maybe not the best for you, and it's also physically hard on me. My voice was hurting, so I'm gonna definitely try and limit the amount of time that I'm gonna be uh, talking. At least not the whole class, right? I think obviously I'm gonna have to talk some. That's what we're all here for. That's my job. But I'm gonna try and work in more ways for us to do some more active kinds of things. And today that means that I'm hoping to finish my yapping by the last hour of the class or so. So after break, after we take our 10-minute break, the last hour is just gonna be focused on helping you all get set up on the homework assignment. So I'm gonna show you how to access the Linux tools that are mentioned in the homework assignment, give you a chance to actually do it before you leave so that you know how to do it and fix any problems that you run into, make sure that you're not getting any bugs, things like that. And then also give you a chance to, if you want to work with a partner, talk to your partner, figure out a game plan, things like that. Before that, I'm actually, so for my hour and a half or so that I am going to be talking, I'm also going to be talking about the homework assignment. I'm going to be talking a lot about what I expect out of the reports and how I want you to present your data. So today is basically all about the homework assignment. Um, I did shift some stuff to next week, but I still think we'll have time to get through everything that I'm hoping to get through, so I'm not too worried about it. One other thing, well, actually a couple other things I want to remind you of. Those presentations are coming up sooner rather than later. Some of you have already reached out to book dates. That's great. I want to remind you that if you don't start booking your date by probably next Monday, because the presentations are only a week after that. So if you don't have a date booked with me by next Monday, I'm going to start doing it myself. So if you want to have control over when you present, let me know. If you don't, that's fine. I don't mind assigning dates. It's not gonna make me angry or anything. Just want to make sure you have the option to pick a date if that's what you want to pick. If you want to have control over that. And then the last kind of logistical thing I wanted to point out before we hop into today's content. Yeah, on Monday's class, I mentioned that I record everything. I'm actually recording right now. I did record Monday's class. I told you I would get it posted the day after class, but I failed. I actually forgot. I have a good excuse. I think I told you that my daughter was turning 8 this week, and her birthday party was yesterday. So I was a very busy dad yesterday. I apologize that I didn't get the video posted like I said I would. I did get it posted today, though, and so I wanted to show you where you can find those videos. If you just click on the date for the class that you want to see the video for, there should be a link right there. I use Canvas for everything. So if you ever want to know where something is for this class, check Canvas first. And if you can't find it, just shoot me an email. I'll be happy to point you in the right direction. But the videos will be there. And the one that I'm recording right now for today will be, right here. And I promise that I will be more expedient about getting that up, especially since a lot of what we're talking about is for the homework assignments. So I definitely want you to have access to that and for the people who aren't here too, especially have access to that as you're working on the homework assignment. So I think that's all the logistical stuff that I wanted to get out of the way. We actually didn't quite get through the last part of this lecture last time. So I'm going to go through this rather quickly, just because we are going to go through MPI in a lot more detail, probably in about 3 weeks, because the final homework assignment 4, or it might be a little longer than 3 weeks, but uh, when we get to the last homework assignment, you'll be using MPI, and at that time, I will bring in a boatload of examples that we'll go through in class. But I do just really quickly want to give you, I still think it's important to give you a brief overview of MPI, just because it is so prevalent, and you're almost certainly going to see MPI mentioned in the papers that I'm asking you to present. It's such a commonly used technology that I think just having some sort of basis of knowledge is important for understanding those papers. So not going to go super heavy into detail, so I'm going to go kind of quick. Um, but we will revisit this topic in a lot more detail at a more appropriate time. So, just a brief recap of what we were talking about previous class. I introduced different programming paradigms. The two main ones that we're concerned about in this class are shared memory programming paradigm, which is pthreads and OpenMP. And then the one that I want to talk to you about now is a message passing programming paradigm, which uses very aptly named MPI message passing interface. As I'm not honestly aware of many other protocols besides this one. I'm sure there are, but this one has such a stranglehold on the usage of message passing, and it's going to be part of almost any supercomputer on the top 500. I would expect to be using MPI in some shape or form to run its programs. So unlike OpenMP and unlike pthreads, we're talking about processes here, right? So we're talking about multiple processes working. And that's because they don't share memory. They each have their own private memory. So there's no, welcome. There's no, easy way for them to communicate other than sending a message. But sending a message, well, sounds kind of simplistic on paper. There's actually a lot of steps that are involved when you think about it. We have to know, for example, how big the message is that is being sent so that the receiver can make sure to allocate enough space in its memory to receive that message. And we also need to know who we're talking to. So where am I sending this message? If I send the message out and the receiver of that message never calls receive, then that message is just going to be sitting there in the buffer and never be consumed. So we need to be careful about our communication patterns, communication strategies, which is something we're absolutely going to talk about in a lot more detail when we get to the MPI section of the class. But just wanted to take a few moments here to give you a quick primer on MPI, because you will again see these terms mentioned in papers. Sometimes they'll even list the exact calls and the exact communication patterns that they use. So MPI init is exactly what it sounds like. It's responsible for assigning processes to their different numbers and things like that so that we know who's who. We then have a way to send and receive, with receive being very important to know that that's somewhat of a blocking call, right? If I say, hey, I'm expecting a message, if that message hasn't been sent, I have really no choice but to sit there and wait for it till it is sent. So that is typically a blocking call, um, and can definitely stall things if you are not careful with it. Although there are asynchronous versions available as well, kind of like a lot of the asynchronous ones where we would I don't think they call it a promise, but that's the term that I'm most familiar with, where we say that we're going to do this thing and we have to come back and check it later to make sure that it's actually been fulfilled. That is also an available option. So here's a simple coding example of MPI where you see they call MPI init to just initialize some variables. MPI com world is talking about all of the processes across the entire system. So I'm asking quite literally, how big is this. Typically, it would be one process per core, but that is customizable. You can tweak that in the options if that's what you care about. So basically, just asking of all of the processes that you know about, how many are there? And then we'll go ahead and just print off a simple message that says, hey, I am processor number 7 out of 12, or whatever the case may be. We're not actually passing any messages here. There's no send, there's no receive. We're just doing some basic setup. But this next example does have some sends and receives in it. So a bit more interesting, a bit more realistic example of API communication. So for the send, we have to say what we're sending. In this case, you can see it's a reference to that number. We have to say, I believe this is going to be, oh my gosh, there's two ones, and I'm not going to remember which one is this. One of them is where we're sending it to. So that would be the process number or rank. This other one represents a tag. So we're actually able to tag our messages so that I can look for messages of a certain type if that's the thing that I'm interested in. I could have that backwards. This could be the tag and this could be the rank. I'd have to check the API for sure, but that's an easy thing to figure out. This is, of course, the type of the thing that we're sending, which is a cue to the receiver. Well, even though the receiver has the same information, how much space do I have to allocate in the buffer to send this message from me to you? And then MPI com world is again the set of processes which we are referring to, we can actually have multiple subsets of processes that we may want to communicate with within the same program. We probably won't be doing that in this class. In this class, we're probably just going to treat the entire set of processes as our set that we're going to be communicating with. So we'll be using MPI comp world for all of that. And then for the receive, you can see it's basically the same information. Oh, this must be actually the rank because you can see that we're receiving from rank 0. And so this is the tag then. Uh, so I figured that out via deduction. Good job, me. And then what to do if we have a problem. This is this last one. In this case, it's just set to ignore. So you can see that obviously if I have a send here, I'm going to need to have a corresponding receive. If you have a program that doesn't have matching sends and receives, probably gonna have a bad time. Something's gonna be blocking and waiting. Some message is gonna be sent that is never received, which is probably not what you want. So it gets very complicated. And just to make things even more complicated, there's lots more than one way to send messages. So the way that I just described is point to point, right? Process to another process. But we can do lots of different message types. So one process can broadcast to every single other process, or we can take a chunk of data and scatter it across, or the opposite, which is a gather, which is kind of like well, reduction, like map reduce, right? Similar kind of idea to doing a map reduce algorithm. We'll explore at least some of these in more detail once we get more to the MPI part of the equation. Again, this is just kind of a quick overview, quick primer. I think I spent about 10 minutes talking about it, which is the topic. So I want to get on the next topic. I'm going to leave you with one final thought here, though, before I switch to my next topic, which is I talked about two primary programming paradigms. The shared memory, so like OpenMP with threads, and MPI, which uses processes. That's an important distinction, right? Threads and processes are similar in some ways, but not the same. And while it might seem like the way I've been talking, we use one or the other, in practice, there's no reason we can't use both. And consider that on a large machine with, what do we say, like 11 million cores is how much the number one machine in the world has right now. At a grand scale, at a big picture scale, it probably looks distributed, right? Lots of boxes that can't really see the other boxes. They can only see what's inside of their box. But within the individual box, it looks like a shared memory kind of system. So a lot of these supercomputing systems are going to be blending these paradigms. We'll be using MPI to manage things on a large scale, but once we get in onto the box level, we might be using some shared memory kinds of techniques to increase parallelism there. It's very common. So, yeah, that's kind of the big takeaway from that one. Any quick questions before we move on to uh, the main gist for today? Do something completely different. Completely different. All right, great. Awesome. So let's move on to what I really want to talk to you about today, which is presenting experimental results. And the reason why I want to talk about this, yeah, I think I already covered this stuff. I think I covered almost all this stuff. Feedback assignments will be in Canvas. This says due the day after the talk. I think that's probably a little bit more strict how I actually feel about it. You'll have a little bit longer than that. But and they'll be quick too. Feedback is not meant to be more than a paragraph or two. It's not meant to be a full-blown paper. The assignment, however, is meant to be more of kind of a full-blown paper style. So let's talk about that. Almost everything that I'm talking to you about this is directly related to not just this homework assignment, but all we're completing this class. So, what should you include in your report? We are kind of striving for research report stuff. Quality, I would say semi-formal is probably appropriate. It's not going to be published, right? We're not aiming to submit it to a journal or a conference or anything like that. That's not our goal. So I'm not too concerned about formatting. If I can read it and understand it, that's good. Don't worry too much about having to match a specific format or margins. That's not worth your effort. Just make it look nice and make it sure I can read it. It should contain an introduction. So uh, this introduction should be very, very short. Especially should include in that introduction specs about the machine that you're using, because that's very, very, very important, right? If you're using the Linux lab machines that we're going to be taking a look at later today, you can just say that because I'm very familiar with those, and that's a pretty well-known system, consistent system. If you're using your own personal computer to do these things, which you are certainly allowed to do if you have a Linux machine at your disposal and you want to run these on your own personal machine, I don't have a problem with that. But I need to know what you're working with. So I need to know, especially, how many cores do you have on that thing? How much memory do you have? Basic specs, right? Do you expect for any machine so that I can put your data in context, and so that you can put your data in context as well when you're composing this report. So that's probably the most important thing to deal with in the introduction. Um, then for each of the problems, so remember the layout of the homework assignment, I think for the first one I gave you 10 prompts, right? But if you're working by yourself, if you're flying solo, you only have to answer three. You get to pick and choose three out of the 10. If you're working with a partner, I think I said five, right? So you don't have to do all 10, but for all of them, every single one, you're going to be designing a little experiment. For every single one, there needs to be some form of data collection. So just pure exposition, just pure, paragraphs is not going to cut it to answer these questions. I need data to back up what you are saying. So you're going to need to design a little experiment. For example, if the question is, how does the number of cores affect the execution of this program? Keep everything else constant, right? And then run it on one core, run it on two cores, run it on three cores, and track execution time, or whatever metric you think would be the most useful to demonstrate the performance of this particular program. And plot that data. We're going to talk about that pretty soon. Show it to me visually, and then uh, provide at least a couple-ish paragraphs of writing to explain those results. So you need to, for every single problem, you need to describe the experimental technique. I wanted to investigate the number of cores, so I used the same setup for every single situation and then varied the number of cores and ran the program X number of times for each core number. We'll talk about that a little bit more later. So I need to know the basic experimental technique. The one I just described is perfect for that problem, by the way. You're welcome to use that setup for the number of cores problem if you're interested in that one. If there's stuff that I've already talked about in class, you don't need to retell that to me. You can assume that I'm already aware of those things, right? You just need to tell me the stuff that I couldn't possibly know, like how many times you decided to run the program, and how you decided to run the program, things like that. So any of those choices that you make, please tell me. But you don't need to tell me stuff I already know. You don't have to explain to me how pthreads work or OpenMP works or MPI works. I already have a good handle on that kind of thing. So not necessary. Then I need you to tell me what the results are, both in visual form and in written form. So again, anything has to be backed up by data. You're going to have to do some data collection. Kind of alluded to this on Monday's class where I said, if you're tweaking the code, you really need to do that first because after you tweak the code, you still got to run it a bunch of times and collect some data. So that's going to take some time too. So make sure you leave yourself enough time to do that. Don't just think that this is going to be a programming assignment where you bang out some code and you're able to ship it in. It's going to be a little bit more than that. So, um, you know, uh, what kinds of questions did you answer? A lot of these questions are open to interpretation. Maybe have a different way, a couple of different ways of approaching them. So try to be clear about what questions you answered, what data you collected, and then what you think the answer to your question is based on the data that you collected. For any graph, for any plot that you give me, there should be at least a paragraph explaining what's going on in that plot in that paragraph. Um, and then in terms of the length, this is a question I get all the time, which I understand. I was a college student. I know how long stuff was that I had to write to. Totally get it. you'll be happy to know that I don't want it to be long. It needs to be as long as it needs to be and no longer. If you think you're going to impress me by writing about something for 20 pages, you're not. You're probably going to annoy me because I will read all of it. And if you just say the same thing in 10 different ways, that's going to be kind of frustrating. So say it once, say it well, move on to the next thing. Don't worry about the length. I will be more upset if something is too long than if it's too short. Although too short is a thing, right? You definitely can be too short. If you give me a sentence, that's very much too short. So I know that's maybe not super concrete in terms of what I'm looking for, but use your best judgment. And if it's really bad, as I said, this first assignment's kind of it's like a training wheels assignment, right? Where the feedback's not going to hurt you too much because we're all kind of new at this, and I understand that. And we'll get better as we go. That's the plan. We're going to talk about graphs in just a little bit. I think I've already made my point for this slide. So let's talk about graphs. This is a terrible plot. Awful plot. I made it that way. Talk about how awful it is. But let's talk about why it's awful. It's obvious. What the heck does this mean? It's not labeled. What is I don't know. The other axis isn't labeled either. There's no timeline. There's no information. What this plot is about. Could be for anything. For ice cream sandwiches, ice cream sandwiches, my 8-year-old ate. Would be a lot bigger. Although 80, probably not 80. That's a lot. But yeah, you have to give me context. Also, the lines between these data points, are those really necessary? Think about what you're implying when you put lines there. If I tell you that the x-axis is number of cores, then okay, the lines imply to me that, hey, there's some meaningful value here at 3.5. But do I have 3.5 cores? Like, that's not a thing. So if you have truly discrete values, then connecting them with lines is not a good thing. And I would say that for most of the stuff that we talk about in this class, there is not going to be a whole lot of stuff in between the numbers, right? It's mostly going to be discrete values on that x-axis. So don't imply that the values in between mean something if they don't. Um, and yeah, let's move on to a better but still not great plot. So the lines are gone. That's good. The axes are here. That's good. We have now not just one dot at every single point, but we have three, which means that for every single core number, we ran the thing 3 times. That's good. One run is not going to be representative of the performance of a program. All kinds of things can happen. What if I hit a cache refresh in the middle of an execution? That's going to happen sometimes. It's not going to happen every time, right? So there will be some variance based on events that are outside of our control. Roger Chamberlain, Dr. Chamberlain teaches this class. Always loves to talk about cosmic rays, right? You never know how many cosmic rays are going to hit your process in the middle of while it's running. We can't control that. It happens, right? And so there will be some variance. This does show us some level of variance, but arguably even 3 runs, not really reflective, not really a great way of demonstrating the variance. And it's cluttered. It's kind of hard to read still, right? It's kind of hard to take away anything meaningful out of this because it's so all over the place. So better because the axes are labeled. Every point is plotted. The title is kind of useless if your title is just the same thing as your axes. You're just wasting my time. I can read the axes and get to the same place. So, okay, let's make it even better still. Now we're talking about average results. All right, the clutter's gone. That's great, but we lost the variation in the process. So I need to know, right? This average, is that in the middle of, a cluster like this, or is it in the middle of a cluster like this, where all the data points are spread? Could be. That's how averages work, right? So there's no indication of variation or variance on this plot. That's a very important thing that we need to be able to see to properly understand what these means are. another example, right? If I go tell my boss that the average on the exam was an 80, then he might be thrilled. But if I then tell him that half the people got 100 and half got 50, then he might be like, so um, you gotta have that variation in order to tell the entire story. Now the problem becomes in how we show that variation. There are a lot of different ways to use it, and the way that we use the variation, or the way that we show that variation, kind of depends on the data that we're talking about. So I'm about to throw some math at you. I'm about to throw some formulas at you, but don't worry. You're if you're scared by such things, well, this is a grad level class. You might be slightly in the wrong place, but even still, it's not going to be that scary because I'm going to boil it all down to practical stuff at the end of this conversation, make it less scary for you. Let's talk about error bars. Student T, students T distribution. Anybody familiar with students T? Okay. It's commonly used. It's great for certain situations. It was published a long time ago, and it's got kind of an interesting backstory. This guy, William Gossett, works for Guinness, and he collected a bunch of stuff about beer, because that's what Guinness makes, and they were interested in tracking the different variance levels of beer, the different batches of beer. They wanted to know, it's not every batch is the same, right? So they're collecting different stats. But Guinness didn't want him to publish that data. They were worried about their competitors getting a hold of it and what they might do with it. But he still wanted to, do it anyway. So he kind of stayed out of the limelight by calling himself a student at a university instead of his actual profession as working for Guinness. And therefore, this is called the student's T distribution, even though the person who invented it was not actually a student, they were just pretending to be one to avoid getting in trouble with their boss. We've all been there before, right? Maybe not. But yeah, at its most easiest to understand level, I guess, we're trying to answer this question. Some confidence level, which we get to choose. We get to pick the confidence level. How close is the sample mean to the true mean? So we're trying to say, hey, we collected data and we got this average, we got this value for the mean. How close is that? How confident are we that that is, excuse me, that is close to the true mean? And we get to choose the confidence level. Typically, we are choosing a confidence level of 95% or even higher. 99% is another common value. The student's T distribution itself is this fun little formula down here where this represents the sample mean, so the mean of all the data points that we collected. If I'm collecting execution time, for example, I would just average the execution time of all of the runs that I performed for that purpose. This is the standard deviation computed in the typical way. Standard deviation is computed and then over the square root of the number of samples. And then this A value is a T distribution. It's really just a lookup in a table. There's no way to, well, I'm sure there is a way to compute that value, but most of the time it's done by just looking that value up in a particular T distribution table. All of that being said, right? I told you I was going to show you some formulas and make it unscary for you. You'll probably never actually have to compute this yourself. Basically, any programming language that you think of, any statistical package that you can think of, it's going to have a student's T function. So Python and all of the um, what is it, Matplotlib and stuff like that. Definitely has a student's T in there. MATLAB has student's T in there. Excel, Microsoft Excel can compute student's T. So this is not something that you're going to have to crunch yourself. You have to plug in your raw data, and then it'll spit out the student's T distribution for you. So not terribly complicated, but still important to know what's going on there. So here's what this might look like if we try and apply the student's T distribution to this. Notice that we've got the number of runs up there in the title, and then these error bars represent that we are, in this case, I think the confidence level was 95%. So we are 95% confident that the actual mean is within these error bars. So the larger the error bars, is more variance we have, because we can't pin down that mean as well. as if our samples are more clustered together. The smaller error bars, we're more certain that the actual mean is at a closer range, closer samples together. Now, there is a problem with this method. Well, it's not really a problem, I shouldn't phrase it that way. There is a restriction on this method. It only works if our data is from a Gaussian, a normal distribution. So the standard bell curve, right? The good news is there are lots of things that follow normal distributions, right? It's called normal for a reason. One of the more common ways that data gets distributed. The bad news is that if you're plotting execution time, which is probably going to be a very popular metric in this class, that is actually an example of one that I would not consider to be normally distributed for some of the reasons that we talked about before. There's a lot of noise that gets injected, noise typically not Gaussian. So we can't necessarily assume that Gaussian distribution. So what that means in practice is that we may have to look at some other ways of presenting our data, or we can actually, I think Dr. Chamberlain would call this cheating, but it's not actually cheating. We're using another famous principle to kind of work around this problem, which is known as, uh, oh yeah, I think I already kind of talked about this. Uh, the method of batch means, that's where I was going with it. And then I'll also talk about some alternatives down here as well that you can use to help us. But let's talk about the method of batch means. Here comes some more scary equations, but once again, I promise, too bad once I break it down, explain the practical implications of all of this math. What we're doing here with the method of batch means is we're taking advantage of the fact that if we have a bunch of averages taken together, that tends towards a Gaussian distribution. So even if I am using something that is not normal distribution, like execution time, what I'm going to do is not take one mean for the entire data set, but rather I'm going to break it up into smaller batches and then take the means of each of those batches, and then that will tend towards the Gaussian distribution, a normal distribution, which then will allow me to use the student's t-distribution on those batch means if I want to. So practically, what does that look like? If you want to use the student's t-distribution on something that is non-Gaussian, let's say I'm collecting 100 runs, right? Well, I'm going to break it up into batches where B is my the number of batches, I'm sorry, and K is how big each batch is. In this case, they would both be 10, probably, right? You want to pick numbers that are evenly divisible. You don't want to leave yourself with odd batch sizes of like 5.5 or something. That would be weird. So you get to pick the batch size. You get to pick the number of runs. You get to pick how big the batches are, and it's all under your power. So what we're doing is breaking them up into different batches and then averaging those batches together. That's what this is talking about, taking the average of each batch, and then we treat those means then as the sample, which is a confusing term because each of our runs is a sample, yes, but we are now taking we're now applying the statistical analysis to the means. So those means then become the samples in this scenario. So that's what we're doing all this fancy math down here, which I'm going to be a very hand wavy about, basically saying that, oh yeah, if I have all of these batch means, then I can average those together to get something approximating data set that I can use students' t-distribution on. I'm not even going to go through all those sigmas. It's not really worth my time. I'm more interested in, explaining how this affects you on the homework assignment. If you want to go this route, which, to be clear, is not the only route you can take. I'm about to explain some other routes as well. If you want to go this route, the value for, let me check my notes here because I don't want to get this wrong. The value for B, the number of batches that you have to have, statistically has been shown it needs to be at least 6 to get to that normal distribution. So you have to have a V of at least 6. 10 is considered to be like Any more than 10 is like excessive. So you don't need to go higher than 10 batches. So think about what that means implication-wise, right? As far as the size of the batches, you get to kind of pick those that yourself. Small batches, of course, not going to be as useful as bigger batches, but you can overdo it because bigger batches is more data collection, which is more time. So, I think 6 to 10 for both of those is not an unreasonable uh, range to work with, then, depending on how much time you have and your ability to collect all that data and analyze all that data properly. So what that would mean practically is, hey, I'm going to probably be running, I don't know, six times six would be at least 36 runs, right? At a minimum, if I go all the way up to the maximum of 10 by 10 would be 100 runs maximum. And then I can apply this batch mean formula and then run the student's t on that. So you would actually have to split it up into batches, compute the averages yourself, crunch that for the student's t, and then you got your error bars. So it does introduce an extra step, or we could try something a little different. So let's talk about other ways that we can plot data, especially data that is non-normal. I guess real quick, well, never mind. I'll pin that thought. I had a thought, but I'm going to come back to it later. Box and Whisker plots. So box and Whisker plots. The important thing to note here is that we're not using the mean anymore. We're using the median. Excuse me. And so the big difference between using the mean versus the median as the midway point is that the mean is going to be more influenced by outliers, by big swings, than the median is. So if I have large variation with lots of outliers, lots of weird numbers, that's going to sway the mean, perhaps strongly, right? Depending on how much of an outlier it is. Whereas the median is not going to be as affected by that case. So for non-normal distributions, bimodal or other kinds of distributions, this is going to be a bit more resistant to those kinds of spread out types of effects. As far as the rest of the box and whisker plot, you can see that the top and bottom of the box are going to be the 75th and 25th percentile. So that's what the box is. And then the minimum of the whiskers and the max of the whiskers is defined as 1.5 times the interquartile range, which is really just the difference between the top and the bottom of the box. So all of that's pretty simple arithmetic that can be computed, which honestly, a lot of times you don't even need to compute yourself. Again, any statistics library that's worth its salt will have a way to quickly plug in a data set and spit out boxes. Might have to tweak the parameters a little bit, but it should all be there. This one was created in MATLAB, I believe, which probably would not be my first choice today. But when I created these slides, I was doing a lot of MATLAB. Have you used MATLAB before? Oh, yeah, interesting. I mean, you're welcome to use MATLAB, especially if you're familiar with it. It would not be a terrible choice. These days, though, I'd probably go with Python. So, but you do you. Use what's comfortable to you. Use what you're most familiar with. Notice, too, that the outliers are anything that falls out of this 1.5 times the quartile range. So, and they get shown to me directly. Don't leave them off. I want to see all the data you collect, even the outliers. Ideally, you can maybe try and explain these somehow. Oh yeah, for this one, my computer fell asleep in the middle of it, and I had to wake it up, and so that's why it took forever. Something like that. But if you don't know, you can at least maybe try to speculate a little bit as to why those outliers are there. But at the very least, I want to see them. It's honestly a little surprising to see graphs that don't have outliers on them. So not to say that doesn't happen, but outliers are common as well, and they should not be left off. And so box and whisker plots are great because, if you are unfamiliar, if you don't think you're dealing with a normal distribution, it doesn't matter because I can see the distribution very clearly just by looking at box and whisker plots. So notice that we have a lot more runs than before. That is maybe one of the downsides of a box and whisker plot is the number of runs that are required. Although it doesn't have to be 100. I think for a box and whisker plot, you're probably going to want, what do I have written here? At least 20 You're probably going to want at least 20 runs for it to be a strong box and whisker plot. Any less than that, and the distribution is not going to be clearly defined enough to draw any significant conclusions from. But you can see that after using this box and whisker plot with a significant number more runs, we can start to see a trend here, right? Where the execution time is clearly trending downwards. Um, that's kind of also what we would expect. We were not able to see such trends in the previous uglier looking plots. Although to be fair, um, I think some of those plots were intentionally junk data, not actual data. So there were no trends to be found anyhow. Um, but moving on to another great plot, histograms. So histograms are very useful for trying to figure out what the distribution is. You can see that clearly here, this looks kind of normalish, right? Based on the way it looks, you can almost see that bell curve there. But the bin size matters a lot. So these are actually the same two data sets, but with this one just having a larger gap between the different bars that are plotted compared to this one. And you can see that while this one is also kind of resembling that bell, it's just a lower definition bell curve. Not as useful, not as easy to draw conclusions from this. So pay attention to your bin size. But the downside of doing a histogram is that this is just for one. So let me go back to show you. This would be just for one of these. So one histogram is just one of these box and whiskers. I can put a whole bunch of box and whiskers on the same plot, but if I wanted to use histograms for each one of these, well, I need to have 6 separate histograms. It's kind of the downside. Can you get that one? Take all space. So I would not recommend necessarily using a histogram for every single one of these that you want to perform. I think the box and whisker plot is a better choice for that. However, if you're trying to demonstrate or justify to me that, hey, this is a normal distribution, and I can use students T on it because look at this beautiful bell curve. Well, that is an argument that I would buy, right? Like you can say, hey, look at this histogram. Clearly, this is a normally distributed set of data. I'm going to use students T on it because I can see this it's a pretty bell curve. So that's one way to, let yourself get to that students T distribution. And the reason I keep pushing it is because that really is, I think, the simplest and easiest way to analyze the data if you can propagate. If you can't, then box and whiskers, I think would probably be my number 2 choice. Or if you want to get really fancy with it, there is in fact a third option, which is called a violin plot. And what a violin plot is, you can see kind of where it gets its name from, right? Because we have the skinny part in the middle and then the fat part that looks kind of like violin over here. This is just a box and whisker plot over here. And the reason why we're showing them both is because the middle part of the violin, the strings part, I guess, it's a box and whisker. So that's just a regular box and whisker plot. And then this guy over here, that's a histogram. So we've taken both of them and combined them together. I can actually see not just the median and the interquartile range, but then also the distribution of all the samples that I've taken on the violin. So these are becoming, I think, a little bit more popular. They do take up a little bit more space than box and whisker plots, but you kind of get the best of both worlds. You get the box and whisker and the histogram all in one shot. So where am I at here? Yeah. Oh, that's just I don't need to go through that one. Yeah. So before I move on to the next topic, let me try and condense it all down for you because I don't know. I mean, I know you're all sitting here just thinking like, hey, what do I need for the homework assignment? So let's break it down. If you think it's normally distributed, students T, please. Think it's Gaussian? Please use students T. If you're unsure, you have 2 options to go with it. You can either check to see if it's normally distributed. There's something called a chi-square test that some of you have heard of. So you can run one of those. That's another commonly found function. A lot of statistics packages. So you can run a chi-square test, and if that works, the results show that it's normally distributed, then students T. I would generally prefer students T if you can use it. I'm not going to say you have to go through the whole batch means thing because that is a bit extra work. You're welcome to. I showed it to you for a reason. So in some situations that might be beneficial. If you cannot demonstrate, if you know for a fact it's not normally distributed, or you just don't know, maybe it is, but I can't tell, or it's just not clear to me based on the information that I have that this is a Gaussian normal distributed set of data. Box and whisker plot is totally acceptable, or that violin plot, but that's also a bit extra. Let's be real. Where histograms are also valuable tools for proving normal distribution as well. But if you're unsure, you might try the histogram and look at it and be like, oh, this clearly isn't normally distributed, so just throw all that out in response to this. So that's practically, I think, implications of what I'm talking today. Is there any questions about that before we move on to the next topic on my agenda? Is that hopefully clear what I'm looking for on the assignment in terms of data collection? And also think about too, I guess one other thing I want to make clear then, what that means um, for this. So for every question, you're going to need to present to me a plot where the x-axis is varying based on whatever we're interested in, right? In this case, it's the number of cores. So for every one of these values that you choose, you're going to have to run it more than once. If you're doing a box and whisker plot, your n is probably 20, say, at a minimum. Students T, I think if it is in fact normally distributed, you can get away with a smaller data set with students T, which is another kind of nice reason to use it if you know your data set is normally distributed. I think an N of 10 or so would be sufficient for students T distribution with the 95% confidence interval. More, of course, being better if you have time to do it. Write a little script or something, right? You don't need to sit there and babysit the computer when it runs 20 times. Most of these programs are not going to be, minutes long in execution. That's not the goal. So you should be able to get through 20 runs in a reasonable-ish amount of time. So write a little script or something to help you collect the data for those runs, and then just cram it into a library function to help generate these plots. Don't worry too much about the math. I want you to make sure you're presenting these correctly. It's important to me, right? I won't stand up here, give this whole spiel if it wasn't important. So please do get it right. If you get one wrong on the first and you use the student's T and I don't think it's appropriate, I'll flag it and I'll let you know. I'll take points off for it, though. We're all learning here, right? We'll flag it and do better next time. That's learning. That's what we're doing. So, yeah, if there aren't any questions, I'm going to move on to talk about some tools because in order to collect the data, we have to have some way of getting that data out of our code, right? We have to uh, have some metrics that we decided we want to look at. And so how do we actually time the execution of a program? What's the most appropriate way to do that? Actually, I think the homework assignment presents a few different ways of thinking about how to time the performance of a program. And ask you to think about that. But there are a couple of tools that are available to you that I would like to strongly encourage you to use. There are others besides the ones that I'm going to talk to you about. And if you really want to use another performance measuring tool that you're maybe already aware of or that you stumbled upon, I'm open to that. Just maybe give me a little heads up first. Don't spring it on me by turning in your report without talking to me about it first. But I am all in favor of exploration in this class, so you're welcome to to go that route if you want to. What I would like to talk to you about, though, are two of the most common ones. In fact, I believe these are both mentioned directly in the homework assignment. And a little bit later on, after break, we're all going to try these out. I want you all to get some practice using these tools before you leave here today, so that you're at least a little bit familiar with them before you start working on them. So the first one I want to talk to you about is gprof. Gprof has been around for a long time. Gprof has been around since, oh gosh, 70s, I think, back when it was still Unix, not Linux, right? So it's been around for a long time. very long time, very well known. It gathers a pretty much standard set of statistics about a program's execution. I don't get to decide what it collects. It just collects the same thing every time, usually related to time. So how much time did each function within my program take? How many times did we call a particular function? How many times do we execute particular lines? So these are things that are, of course, very useful when analyzing the performance of a program. It's pretty coarse though, so there's no flexibility. I can't collect other data. This is what I can do. If I care about execution time, then great. If I care about number of function calls, then awesome. If I care about number of cache hits, too bad. Not going to do it for you. But we've got other ways of doing that that we'll talk about in a little bit. The way that it works is that it instruments, so it actually inserts lines of code into your code that report back to gprof every time they get hit. So think about the downsides of that, though, right? It's literally inserting extra lines of code that have to be run, so it's like the execution time a little bit. They, of course, try to keep it as lightweight as they possibly can, but you can't make it zero, right? It's the classic. The more you measure something, the more effects you're going to see of that measurement in your results. So that can be something you can tweak the number of samples that it takes, and that can, of course, help with the overhead required for performing these measurements. But you're going to have some performance hit when using gprof, and I think that's kind of one of the questions, right? Uh, I think the question is phrased as, what can we learn about gprof from this code? But really, well, there's a lot of different ways you can interpret it, but one way you can interpret that is how much overhead is gprof inserting just from measuring, right? Think about how you would design an experiment to determine that. Try and run it once without gprof, time how long it takes. Well, how would you do that? You have to figure out some alternative. I'll leave that to you. And then compare it to what gprof says the times are and how different are they? That would be an example of a way you could answer that question, right? One of many. But let's talk about how to use gprof. In order to do it, we have to pass in special compiler flags. So these are baked right into the GCC compiler. You don't need to use the wall flags if you don't want to, but it does show you all the warnings and stuff to make sure you're not doing something totally crazy with your code. But the PG flag is what tells it that you want to instrument your code with all those gprof samples and such. And then you just run the program normally. When the program is finished, it spits out this gmon.out file. I'll show you that a little bit later once we actually take this thing for a spin. And then you have to use the gprof program to analyze that gmon.out. If you open that gmon.out file yourself, you're not going to understand anything that's in there. It's not for you. It has to be interpreted by the gprof. So I'll show you how that works just a little bit. And it spits out two different things. The one's called a flat profile, and the second one is called a call graph profile. Let's take a look at an example of those. Here is the example code. Actually, we're going to be running this code, this exact code here after the break. Once we take this stuff for a spin. We've got two functions, and these functions don't do anything, not anything useful anyway. The most important parts of these functions to pay attention to are these for loops, which are written to just spin for a very long time. Basically, I just wanted to make sure that this program was running long enough that we could get some useful data out of it. So we're not computing anything useful. The first one spins for a long time. This one spins for slightly less time, but still a really long time, right? The main method also spins, but the number of F's here is, there's only 6 compared to 8 up top. So this is a lot less. And then we have another function over here, which you can see is very long. So all three of these, very close to the same number of iterations, right? The main method has a lot fewer number of iterations. And here's how it would be compiled. Again, this wall flag is optional, but is useful for showing all the warnings. And then this is how we would run it, of course. And then this is how we would analyze the results. it has it redirected into a text file just so that you have a copy of that for later, which is maybe not a terrible idea. But you don't have to do that. It'll just spit it right onto the console if you want to as well. I'll show you that a bit later on. And so, what would the actual results look like? Um, the flat profile, sorry, is going to show us the name of all of the functions that were called, as well as the amount of time as a percentage. So it's not going to say specifically, well, it does say specifically how many seconds is spent, but it also says the percentage of the total execution time as well. So I can see the relative amounts. And then these sub-seconds indicate how much time is spent actually executing lines of code that are in this function, but we also have how much time is spent in the any child functions that are called as well, because functions can call other functions. And even though I'm in function one for a long time, well, some of that is probably because it called function two and spent a long time in function two, and we don't necessarily want to count that time against function one, even though technically function one is still waiting for function two to return, still active on the stack and all that fun stuff. So here's what the flat profile would look like for a sample execution of that code I showed just a few slides back. We can see that these three functions with the giant loops are taking up the largest chunks of time. A little bit of difference there. You can see they're each taking up about a third. And then the main method, which had the smallest of the four, you can see is drastically smaller, just a fraction of a second, just a fraction of the execution time compared to the ones that were arbitrarily spinning for a lot longer than that. You can also see, though, that because function one calls this new function one, that the total for this one is 18 because it's including both of its times. But these columns also show that, oh, the actual time that I spent doing stuff inside of it, half that time, the other half is spent that function call, right? So it helps you break that data down. These are all explained too when you run the program. It actually will tell you the definitions of all of these. So you don't need to necessarily have them memorized. The call graph profile groups things by each individual function. So it shows who called that function, how many times that function was called, and then what functions did it call, how many times did it call all of those functions. And so an example of the call graph profile looks something like this, where we start with the main. See how it's, unindented compared to the other ones. So the top section is about the main method, which calls this function and calls this function, and it calls each of them one time, right? The amount of time that was spent in main is right here. The amount of time that was spent in functions called by main is listed in that column. So you can see that the vast majority of the time was actually spent in those other functions. And so then down here in this second block, this is the block representing this one. So it was called by main, but then it called this new function after that. And 66.7% of the time was spent in this function. But again, if you look at the breakdown, this is the amount of time that was spent directly in this function, and this is the amount of time that was spent in the child functions that were called. So it truly wasn't all of that time spent in functions. Some of it was because of that other function call below. And you can see, the final two blocks. So each function in your code gets a block. There are four functions here, so that's why it was blocks, and you can interpret them based on which functions you care about the most. The number of times a function is called in this example, kind of not super useful, but if it is being called a lot of times, that is useful information to have, and probably one of the more common reasons why I use the call graph is specifically to see, okay, how many times did this function get called? Because that provides a lot of context to how much that function is impacting the execution time of our program. So that's a useful thing to know. So very basic. gprof, very basic. which is both good and bad, right? It's simple, it's easy to use. It is on any Linux distribution that you could possibly think of, so it's readily available because it's kind of been around for so long, right? So those are all good things. But if you if you suspect that your problem is due to um, like caching or some other effects, uh, you're not going to figure that out here. This isn't going to help you make those determinations. We need other tools to help us with that. So yeah, what other limitations do we need to talk about? Sampling. Sampling is inaccurate just by its very nature, right? If I have one function that runs for a long time and another function that runs for a short amount of time, but it gets called a whole bunch of times, then the sampling is maybe not actually going to reflect how much time is spent in that small function because it's easier to skip over it with a large sample rate. So getting that sample rate right is tricky. You can change the sample rate, although I typically just use the default one of 10 milliseconds. It works well for most situations. Um, Inline functions, forget about it. It's not going to help with gprof. Gprof is not worked well with inline functions at all, which means if you've optimized the crap out of your code, gprof is going to have a hard time helping you with this. That's a pretty common problem that people run into actually on these assignments. There's compiler flags for optimization levels, right? -O, and if you crank them up to 11, there's not really a 11. But if you crank it up to the highest optimization level, gprof starts to struggle. Because from the perspective of gprof, it just looks like everything's in one big long function. And you can't tell where the functions are anymore because they've been all optimized out. So you have to be careful about that. And then, particularly for our purposes, parallel programs also struggle because it has a hard time keeping track of the different threads that exist. It's really meant more at the process level. So if you spawn a bunch of threads, it cannot adequately track them all and reflect the execution time of all those different threads. So we need other tools for those purposes. So let's talk about one of them. Perf is the other tool that I want to make sure you get a little bit of practice working with today, get a little taste of today. It's another one that I think was mentioned directly on the homework assignment to use. This one is a lot different than gprof in that it's just counting events. Actually, a lot of these counters are happening whether you ask for them or not. They're baked right into the kernel. The kernel is counting all kinds of events for logging purposes and, you know, uh, all who knows what. But normally we don't we can't even see them. Actually, they require a certain level of access for us to even see. But if we do want to access them, we have to use a tool like perf to go find those counters and show them to us. So there's lots and lots of different counters. The list is seriously just absolutely massive. And I couldn't even tell you what all of the different event counters mean. I know what some of them mean, what the ones that I've used mean. You can, of course, look them up if you need to. Some of the more common ones are going to be processor cycles, which I believe is the event that's by default. Now, be careful with that. Processor cycles might lead you to think that you could somehow translate that into time, right, in seconds, but not every cycle is created the same. I know they stamp it right on the chip that it's, what, 2.4 gigahertz or whatever the number actually is, but that doesn't mean it's going to run at that rate constantly. It fluctuates, it goes up and down. So number of cycles is not a direct relationship to execution time. They're related, yes, not going to deny that, but you can't necessarily get execution time from number of cycles and vice versa. The math just doesn't work out that way. Still a useful metric, though. Still an example of how much the computer is expending effort on a particular part of the program. So still useful in that sense. Cache hits and misses, context switches, system calls. One that I like to look at is branch prediction. I'm a big hardware guy, so I love things like pipelining, branch prediction. So how many times did I predict that I would predict branch what I was for? I had to actually go back and figure it out all over. That takes time, right? If I predict it correctly, I just save myself a bunch of hassle. But if I predict it wrong, whoops, pay the penalty. So how um, could be an interesting thing to look at. So perf. gives us the ability to just view these counters. That's really what it's for. You tell it which counters you care about for a particular program execution, and it shows them to you. So um, we'll take a look at the list of ones later. Perf stat is how we are going to run the program and collect those statistics. We don't have to do any different. So unlike GPOP, need any compiler flags. That's a good thing. I don't necessarily like having to recompile my program just to collect information about it. Perf record puts things into a file, which you can then use the perf report command to analyze. Because once again, that perf.data file, you can look at it, but you're not gonna know what it means. It's not for you. The perf report command is what's gonna be more human readable. So that's what we use to analyze those data files. But it's still nice to be able to have that data in a file because you can do a bunch of runs, stash them in a file, and then you don't even have to analyze them on the same machine. You can put those files on any machine that has perf and analyze them at your leisure. So it's kind of the nice way of doing it that way. So let's talk about events. I already mentioned some of them, but holy cow, there are so many. Looking at the hardware side, we see, oh yeah, here's branch predictions, number of instructions that were executed, how many times I went to the L1 cache, how many times I went to the lowest level cache, and how many times I missed the cache when I tried to look there and had to go fetch it from memory. Those are all kinds of statistics just on the hardware side. Then on the software side, we of course have the number of cycles. Well, actually, that's more hardware side. I don't know why I said that on the software side, but page faults. You know, um, what else do we have up here? How many times did I have a blocking call come in, right? That forced me to take a break. How many times did I context switch? Things like that are all going to be types of counters that we can use, some of which are not relevant to us, right? We're not doing a whole lot of networking in this class, so accessing the Ethernet port probably not super useful to us, but in other situations might be very useful. So Perf tries to do it all, and it does a pretty good job, I have to say. So I linked a perf tutorial on the website. I believe you can find it right there on Canvas. And I am pointing you to that because I have just scratched the surface of this tool. I promise you, there's so much that it can do, more than I have time, more than I really want to spend time talking to you about. You are going to have to do a little bit of digging if you want to use this tool, which I think is worth the time, worth the effort. I've encouraged you to do it. We'll actually take a look at how to run this a little bit later once we get to that point, and we're getting closer and closer to that point. Um, any questions on the tools before I talk about the presentations? We're almost through. 5, maybe 10 minutes. We'll take a quick little break. Before that, though, I did want to spend a little bit of time talking about the presentations because I know this is another thing that's coming. Um, summer session feels so weird because normally we would have longer time before the presentations are coming up, but everything's so crammed together. So they're sneaking up fast. It feels like they're sneaking up really fast, to me anyway. But uh, make sure you choose a good topic. Those papers that are listed are pre-approved, so you don't really need my approval for that. But if you want to pick a different one, at least let me know which one so I can give you a thumbs up or thumbs down. You have to pick and choose what to present. So you don't have to tell us everything. Pick the most important parts, and then don't hesitate to be critical either. Tell us what you don't like about it. If you see any flaws, even published papers have mistakes, right? Nothing's perfect. So if you see any flaws, be sure to tell us about that. That's interesting stuff. And then in terms of the organization, so do a lot of you have presenting experience? Okay. Yeah. So I do regularly deal with students who are not given a whole lot of presentation. So I think it's kind of important to just go through some basics real quick in case that applies to any of you. Um, your audience is the people in this room. So not my mom who doesn't know anything about any of this stuff. So you don't need to be super, super slow and super pedantic about it. You can assume that we already kind of know what's going on. Not everything. We haven't read the paper, so don't assume that we've read the paper. In fact, I would venture to guess that if you are presenting on a particular paper, you might be the only person in this room who has read the paper, with the possible exception of me. I've read some of them, but not all of them. I usually try to read the papers that students are presenting on, but I don't make any guarantees that I'll actually have time to do that before your presentation. So even I may not have read the paper that you're presenting on. So don't assume that we've read the paper, but assume that we kind of know what's going on, right? Assume that we are your audience is fairly familiar with general, computer science C kind of stuff like computer architecture, big O notation. You don't need to explain that to us. At a grad level class, most people should already kind of know around that. Try to decide on what your points are, what your main takeaways are first, and then organize your presentation around that. Um, it may not match what's in the paper, and that's okay. Please pull figures from the paper. Please, at least some of your slides should have figures directly from the paper because those are so great at illustrating the data that was collected, the story that it tells. So you don't have to pull all the figures from the paper. That might be a bit over, but definitely pick a few of the more important ones, the ones that reinforce the message that you're trying to tell us with your presentation, and make sure to include those. Know what the message is for each slide. A good rule of thumb for this, I typically try to have, if I have a slide in my presentation, I'm probably going to be talking about that slide for at least 1 minute. If you're blowing through slides faster than that, your audience isn't going to have enough time to process the information you're trying to get on that slide. So that means that for a 30-minute presentation, you should not have any more than 30 slides. If you walk in with more than 30 slides, that is an immediate red flag to me, like, uh-oh, some of these slides are going to be gone in like 5 seconds, right? And that's not good. So slow it down. You don't need tons of slides. I would say less can be better, right? Even for me, I've been talking for almost at least an hour, and I've only gone through 29 slides well, I had a few more before that, but still, right? I'm at like 2 or 3 minutes average per slide. So that's not a terrible ballpark to be in, which for a 30-minute presentation would be 15 to 20 slides, right? So aim for that kind of ballpark. If you really need some help, if you're really nervous about the presentation aspects, come talk to me about it. I will definitely try to help. I don't want to necessarily like pre-approve your slides or anything, but if you're really feeling nervous about it, I'm more than happy to take a quick glance at your slides and try and give you some brief feedback before the presentation, just to help. I don't want anybody to fall on their face up here, right? That doesn't do any good for anybody. So if you're really nervous, if you're really worried about it, and you need a little push from me, a little encouragement from me, I'm more than happy to give that to you. I'm not going to pre-grade your presentation, though. That's kind of the point I'm trying to make. You still need to get up here and deliver. You still need to get up here and do this stuff. So yeah. And then the questions. So you're going to, as I mentioned, some of you are going to be selected to review, provide feedback on these presentations. So for the people who I select, which again, not everybody has to review every presentation. Only a few of you are going to have to review each presentation. So each of you is only going to have to review 4 presentations total. 2 for the first batch and 2 for the second batch. And so for each one of those reviews, these are what I ask you. It's the same. It doesn't change. It's the same every time. Describe the major contribution of the paper. That's basically just proving to me that you were here and paying attention, right? If you were here and paying attention, that should be an easy, no-brainer. Then, what did you think the presenter did well? And what do you think the presenter could improve on? Not the paper, the actual presenter. That's it. It's that simple, right? It's that simple. It's that straightforward. Being able to talk about stuff is important, especially if you're getting into research, which I know not all of you are researchers, but this is a graduate level class, so that's kind of the realm that we're in, right? Being able to talk about this stuff is important, even if you're not doing research. At work, you talk about technical stuff all the time, so being able to have those conversations is important. So I'm trying to get you practice doing that, trying to help you build those presentation skills. That's the purpose of the presentations and of the providing feedback. And I will also provide this feedback for all the presentations. That's my job. I'll be sitting right up front taking notes. And I'll also try and ask at least one question of every presenter during the the Q&A. I always try and think of at least one question, maybe even more. I'm not trying to grill you. A lot of times I'm going to try and maybe throw you a little softball because, you know, again, I'm not trying to make anybody fail. I don't want to see anybody fall on their face. I want these presentations to be good. So hopefully that helps dispel some anxiety about the presentations. I know that there is generally some anxiety about them. I can't make it all go away. I'm maybe one of those freaks of nature who doesn't mind speaking in front of crowds. That's kind of why I do this for a living. I get up in the intro class, I have 300 people, and I get a little nervous on the first day. As soon as I get up here and start, it's all gone. So I'm not promising that I can do that for you, but a little bit of exposure therapy helps with us getting through scary things. So you all can do it, I promise. It's meant to be a good thing, meant to be a skill building thing, not a scary thing. So any questions for me about that or any of the stuff that I have covered so far today? Yes. Um, No, but I'm also not going to sit here with a stopwatch and take points off. If you ended 10 minutes and be like, they read the whole paper? Like, right? But if you're a few minutes short, aim for 30, and if you're plus or minus 5, you did. Good question. Any other questions? Address? All right, let's take a break. I know I need to grab a glass of water and hit the bathroom real quick, so let's take a break. I think it's almost exactly 10 till, which is perfect. 6:49, yeah, 7 o'clock. Let's take a break until 7 p.m. When you get back, a lot less of this, still a little bit of this because I have to help explain how to get access and stuff. But when you get back, I hope you brought your computers. If you didn't bring your computer, that's okay. I'll do a little demo. Just watch along. For now, you can take some notes so that when you get back to your computer, you'll hopefully have a good idea what you're doing. But I really want you to try out some of these tools today. You can work with a partner too if you don't have a computer. That's totally fine. And yeah, give you some time to get started on the homework. Ask any questions you have about the homework assignment. See you in 10. Go with that. Uh, cool. Yes, I am recording. All right, great. Let's do some stuff. If you brought your laptop, that would be now would be a good time to get out and practice. If you didn't, maybe find a friend or neighbor to hang out with, or just sit back and watch the screen because I'm recording all this stuff, and you can use the video to follow along at home when you get back to your computer. No big deal either way. I am basically going to run through the process to access the Linux lab machines, which have both gproc and perf available for you to use. As I as I mentioned, you're welcome to use your personal machine. So gproc should be on there by default. Perf you may have to install through the package manager, which is totally okay. Let me know if you need help doing that. But if you don't have access to a Linux machine or you don't want to bother with all that stuff, please use one of the Linux Labs machines. They are not terribly difficult to get up and running. So let's go ahead and there's actually two different ways that you can do this. So one way, if you are comfortable using the terminal, which you're gonna have to use the terminal for both options, so I don't really know why I said that. Uh, if you just want to use a terminal to SSH in, so make a remote connection to one of the Linux Labs machines, uh, excuse me, you can do it that way. Or alternatively, you can fire up excuse me, a Linux lab machine through your browser. So there's a link to access a Linux lab machine through the browser. Maybe some of you have used that for some of your other classes. I'll show you how to do it both ways. I personally prefer to do it using SSH, but if you prefer the web browser route because it's a bit more visual, I have no problems with that at all. The instructions also are right here in the homework assignment itself. So I'm going to go ahead and pull that up and kind of use that to help me follow along. So option number one, you have to use SSH to access this particular web server, shell.cec.woostle.edu. And this needs to be your Woostle key. It should not be Woostle key. It should be your username, your WashU username, whatever that happens to be. Mine is dshook, right? Yours is probably some variation on your name as well. That's typically how it's done. If you're on a Mac, you have SSH already. All you got to do is fire up a terminal and run the commands, making sure to substitute your key in for that. If you're on a Windows machine, you do not have SSH by default. Windows does not ship with SSH. So you have two options. Well, you probably have more than two options, but the two options that I'm most familiar with would be to download an SSH tool, PuTTY being one of the more common ones. I believe they don't actually have boxes in this room anymore. The lab next door does have boxes in it. So they have PuTTY on already. So if you want to use one of those, you're more than welcome to, or you can download PuTTY on your own personal machine. The second route, which is the one that I'm going to be using, would be to install Windows Subsystem for Linux, which is basically going to give you a Linux command line on your Windows machine. I think it's fabulous. I use it for all kinds of stuff. Windows command line, it's crap. So, I would strongly encourage you to consider using Windows Subsystem for Linux anyway, just because it's cool and wonderful to have, and has really changed the way that I use my computer quite significantly. So I've already got it up and running here. This is not a Windows command line. This is a Linux shell installed through my Windows machine. So I would go ahead and SSH in using my Woostle key, shell.cec.woostle.edu. It's going to ask you for your password. If you're not super familiar with using the terminal, it's not going to the cursor's not going to move. It's going to look like your password's not being typed in, but I promise you it is. So type in your password and hit return, and hopefully it will log you in, which is good. Now, if you actually tried to run gproc here, it exists, right? I didn't actually compile the code to use it or anything, but so it's telling me I can't find the output results. But gproc is here, but you don't want to use gproc. This is a public server that's going to have many people logged onto it. In fact, if I wanted to right now, I could type foo and see that, oh, hey, all of you are logged onto this server right now, right? Because you're following along with me. So what does that mean? If I'm trying to run 20 runs and you're trying to run 20 runs and you're trying to run 20 runs, what that's going to have big effects on our results, right? Versus if I'm the only one who's on there, we get totally different results. So we need to access a specific machine, which the school has a big old cluster of them. I don't even know physically where they're located. They are on campus. I know that. I don't know where. I've never actually seen them in person. I've only accessed them remotely. So in order to get access to one of those machines, you have to use this big, scary looking command. And this can go wrong. I've already had more than one student reach out to me saying that they've had troubles trying to run this command. I tested it today and got it to work, so I am confident that it will work. I am a little bit concerned that copy pasting might be part of the reason why people are struggling. You may have to do the tedious thing and actually type it out. I'm worried some of those characters may not translate properly. But another thing to keep in mind, let's break this command down real quick, right? So srun is the command that is going to connect us to the Linux lab machines. That's what the machines are called on campus. This -c flag stands for how many cores do you want? So if you are running an experiment, running a problem where the number of cores matters, choose that number very carefully. You can go up to 8. So 8 is the max. 8 is the max number of cores that you can request. So if you want to verify performance versus number of cores, then please take 8. Also, while on a little side note, if you want to verify performance versus number of cores, don't stop at 8. Go up to 12, go up to 16. See how it works when you exceed the number of cores that you have too, because I think that's important to look at. Yeah.
Like, if we were all trying to grab eight at the same time.
There is, but it's higher than if we all tried to grab 8 at the same time, I'm pretty sure. I want to say it's in the hundreds total, and I guarantee that we're the only class using this thing over the summer. If we were using it during the semester, I might be a little bit more concerned about that scenario. But for the summer, if it's literally just the people in this room, plus maybe 1 or 2 people who aren't here today, we're not going to hit that ceiling. So good question though. Yeah, good question. Good thing to be looking out for. So yeah, request a number of cores. For some of the problems, 1 core might be enough, right? If you're not investigating performance versus cores, then okay, whatever. You only need one might be fine. For the job name, this is kind of a placeholder, so I almost always replace this, and I almost always just use my Wustel key so that whoever's looking at it knows that hey, that's my machine. Dang it! So it's not yours, it's mine. So I almost always replace that with my name or Wustel key. And then this part is very important. There are some machines that are reserved for research purposes, some machines that are reserved for academic purposes. So we cannot request the research machines for hopefully obvious reasons. This is saying we want to access one of the academic machines. That's what the dashing engineering class is for. And then the final option here is saying that we just want to open a bash shell once we get to that machine. So hopefully this command will work. If it doesn't work, we'll see. All right. And this is actually the error. This is actually the same that I've seen from a couple of people now. Again, I think it's a copy paste issue because I promise you I did this just today on my machine and it worked no problem. So I'm going to do the fun thing and manually type it out and hopefully it will actually that might be something worth trying as well. Good question. Did it work? Oh yeah, you cracked the code. You don't need the $sign. Yeah. I had suspected it had something to do with that job name, and I didn't nail it down. You beat me to it, so kudos to you. Take the $sign off of there. I will actually probably go and edit the homework instructions when I get home to take that off. Yeah, $2.
Insert.
Wow. Well, now I'm just really confused.
We're being big no.
Yeah. Okay. We're having fun, aren't we? Yeah. I love it when errors aren't reproducible. It's always a good time. I don't know. You know, uh, I know a lot about computers, but IT doesn't give me any more access to these things than you guys, really. Seriously do not have any more permissions or privileges on these boxes than you all do. So I can't get in there and look at the logs and see what the heck's going on. I might email IT because it's confusing and slightly annoying. If it becomes a bigger problem, I'm definitely going to email IT and be like, what the heck's going on? I almost emailed them today and then I tried it and it worked. So I was like, oh, I don't have to. But now I'm like, maybe I do. But hopefully you don't run into too many problems. Now, at this point in time, you're welcome to do whatever you want. So this is where you need to collect the data on one of these boxes. You're insulated from everybody else. So nobody else is going to be sharing this machine with you. This is your machine. However, once you log off, poof, right? Actually, I don't think it poofs right away. I think there is a timeout. So if you log back in fast enough, you'll get back to where you were. It doesn't lose your files though. The files, any files that you get created actually will be saved onto your user space and they'll be there the next time. Yeah.
Same machine or will it serve another separate work?
If you use the same job name, so the job, that's where the job name comes in. If you use the same job name, I believe you will be connected to the same machine. If you don't, if you use a different job name, it's gonna spawn up a different machine for you. I'm pretty sure that's how it works. Yeah. So remember your job name. That's why I just always use my name.
So if I had some chance chose the same job name, we would both be connected. And we would both be able to say, using the boot name, we would both be able to see that one.
I think so. I've never actually tested that, so I'm not 100% certain. But logically, yes, I think so. Yes. Um, there might be some permissions errors in there. It's like, so if you created the job, then you're gonna have the, access to it. I don't know if someone else who didn't create the job will have the permissions to log into that machine. You hear what I'm saying?
Yeah.
So that's what I'm a little unsure of. But I don't think it should matter if you're working with a partner, right? You can easily spin up your own box. I mean, chances are you'll be working on different questions. Like so, yeah. Not necessarily, no. Um, I mean, if you're working solo, I don't think it matters all that much, right? Because yeah, I'm only gonna need one machine at a time anyway, right? Um, I can see the value in having one machine shared across two people if you are working with a partner, but I also don't think it's gonna prohibit you from getting the work done if you don't do that, right? So using these two separate ones is totally fine. And as we'll see when we look at the web version too, it actually will show you all the machines and when they're gonna expire and stuff like that too. It might be a little easier to work with that way if you're worried about issues like that. Anyway, at this point in time, we can do gprof, but remember we have to do some other stuff before we can properly do gprof. So we need some code first. I think I have the code from here already, right? Test gprof.c, but you all don't. So that's the tricky part. And actually, that's one of the things I was realizing could be a potential issue during the break. And I was trying to do a little bit of research on how to get a file, like the homework files, onto one of these Linux lab machines in as simple a way as possible, right? So for this example that I want to look at right now, I think the easiest way, by the way, just go to the calendar page, you'll see a link, testgprof.c is quite literally that code, is the exact same code that I showed you um, from before. So this one, since it's just the one file, a copy paste into a file on the Linux machine will work just fine. But you're doing it via command line, right? So that means you're gonna have to use Vim or Emacs. I saw somebody shaking. You're an Emacs guy, maybe, or yeah, yeah.
No.
I know how intimidating Vim is. I'm a Vim guy, so I love it. I'm used to it. but use Emacs, use Nano, use whatever, or if all of the above scares the crap out of you, that's what the web version is for, right? Because that'll have a nice visual text editor that you use. I'll show you how to use that in just a second, right? In fact, actually, maybe I should show you how to do that now, since we're on the topic. Because if we go back to, oh, that's not the right tab. If we go back to the homework page and scroll down to the Linux Lab link right here. This might help us answer some of the questions y'all were asking too. This is the page where we can spin up a machine through a web browser. So the way to do that is to go up to My Interactive Sessions, and then we want to create Academic Linux Desktop. We don't need a GPU, at least not for this assignment. Maybe on later ones, we might want one with a GPU on it. But for now, we don't need a GPU. So we're going to click on Academic Linux Desktop. And then, you can pick a different flavor if you want to. It doesn't really matter. Here is how long it will last for. So if you're worried about it going poof and disappearing, well, I don't know what the max number of hours is. I'm sure there's some limit where IT's gonna be like, no, you can't have that for a year and cut it off. But if you wanted to keep it for, a couple days, I don't think they're gonna complain about that too much. I've never tested to see what the max limit is though. So is it 8? Oh, you just figured it out, huh? Okay. 8 hours then, apparently. I know 8 is the max for the number of cores, but you put a big number in and said can't do it. Oh yeah, there you go. Question answered. Yeah, I don't need 8 hours. I don't even need 1 hour really, but that's fine. And then go ahead and click the launch button. Uh, this is the one that I fired up earlier today, just to kind of test it out and make sure everything was working. This is the one that's firing up right now. It takes it a second to fire up. It doesn't fire up right away, but as soon as it does fire up, it will show a link that you can use to connect to it. So it's starting now, and now it's running. Hooray! And now we can click this button here to launch the Academic Linux Desktop, and boom, we've got ourselves a Linux machine right here in our web browser. So this actually makes it so much easier to get files on from Canvas, for example, because right down here is a web browser. Hello? Yeah. Oh, I did it twice. My bad. So right here's a web browser. So, go to Canvas, uh, log in to the Canvas page. No, I don't ever save my password. And now we can go download the files that we want, which for today is really just that one on the calendar, actually. And I'll download the homework one file a little bit later as well when we get to that point. But for right now, I just want to download this guy. So click on here, download it. Poof. Okay, I'm gonna give y'all a minute to catch up to me. Everybody got the file working on it? Good. All right, perfect, wonderful. Now that we've got the code, let's take it for a spin. So I'm gonna fire up the terminal down here. Now here is here's the fun bit. We still actually have to run that srun command from here as well. It actually isn't going to work right out of the box. The reason for that is because the perf command requires kernel access. IT doesn't want to just give kernel access willy-nilly, so they make you jump through a few extra hoops to get it. So once again, we have to do srun, that whole long thing. It's actually the same command. So let me pull it up on all right, close the tab. Dang it. Here it is. We still have to, whoops. No, we still have to, we still have to SSH first. Oh my gosh, I almost forgot that step. So it's actually exactly the same process, just doing it through this machine. So SSH into shell, just like we did before. Okay. Something might be doing, well, I'm not going to worry about that. And then we need to do the srun command with all this fun stuff. Dash P Linux lab, dash C1. Oh my gosh. Dash J job name without the dollar sign question mark. A engineer. I noticed that through the host name, but we still need well, I guess I could be wrong, but we'll find out here in a second. When I try to run this command. Class any P2. Okay. Oh, fun. Well, hold on a second. Okay, you know what? I think I lied about that because you're right. It does have the same host name, so I don't think I actually need to do the srun command. I just need to do. I did need to do the SSH in the shell though. No, actually, I don't know that I even need to do that because that's the same host name. Okay, I'm sorry about that. I obviously there were some gaps in my knowledge as to how this works. It seems like I actually don't need to do any of that stuff. Just the Linux lab machine out of the box is fine. So forget everything I said in the last 5 minutes. My bad. Um, but if you do run into problems with that, please let me know so that I can get out to IT and get these kinks worked out. Uh, if you can't tell, they change things every semester on me. So I've used this system, but it's not the same as it was even last semester. And that's why I'm still kind of fumbling around with it. I apologize. But I do want to make sure I get it right for y'all. All right. I'm going to assume everything's working. gprof I know is going to work. So we just need to figure out where that file is. And it's probably in our downloads. So go into your downloads directory and there it is. Hello, hello. So our next step then is to compile it, and we have to compile it, remember, with that special flag, dash PG. Can I make this text a little bigger so y'all can actually read it? That would be useful, probably. All right, there we go. Dash PG, and then we're gonna do the dash O test gprof test gprof.c. And these are just warnings. I know they look scary, but they are just warnings, and we're all good programmers here, so we know we can ignore warnings, right? That's what they're for. Um, they're not going to stop us. So, okay. Next step is to run the program. So /test gprof. And it's going to take a second because remember, I put those loops in there that are going to spin for a significant number of times. I mean, the call graph I showed earlier said it took like 27 seconds, right? So it is going to take a few seconds to actually run through this. And while it's doing that, gprof is sampling, right? It's doing its thing, sampling and keeping track of how many times each of these functions gets called, how much time we're spending inside each of these functions. And then eventually it's done. All right, we're done. And if we take a look at what files we have now, we see that we have yes, our code and our binary, but we also have this file called gmon.out, and that's the file that contains the data. So in order to analyze that, we need to use the gprof command with the name of our program, test gprof, and the name of the output file. And then it spits out our results. If you scroll back up to the top, we see the flat profile first. We got different numbers. It looks like it's running a little bit faster. Looks like I saved about 3 seconds compared to what was on my slide. But the breakdown in terms of percentages is roughly the same, just right. So that's our flat profile. I don't need to go through that all again. You can, of course, read the documentation that is listed right here if you need a refresher on what those mean. And then here is the call graph that shows how many times each of these was called and how much time was spent. Anybody having trouble? So is everybody able to do this who tried this? There'll be time too, after we're done here in a little bit. I can help you out if you're getting stuck. The other thing though that I wanted to show you is how to run perf real quick. So let's take that one for a spin. Now, in order to run perf, we need to do, well, first, let's take a look at perf list. Remember, perf has a huge list of counters available. So how many counters? Oh, terminal's not fully functional. Well, thank you for that. Um, here's all the counters that are available. Ah, why can't I scroll? Why can't I scroll? Something's not working right. Oh, okay. Here we go. I just have to hit return to scroll down. It's a long list. Um, I almost never use this command by itself. I'm almost always going to, you can hit Q to get out of there, by the way, if you feel like you're stuck. I just wanted to show you how many counters there are available. And again, I don't know what all these are. There's so many. So, if you're interested in a particular topic, what I would recommend that you do is honestly go find the list online and use Control F in your browser to search the list for the counters that seem like they might be relevant to you. Or if you really want to do it via the command line, then do perf list, but then pipe it into grep and look for, I don't know, L2 or something like that if you're interested in L2 cache, and it'll show you, all the counters that are related to the L2 cache, right? Um, Looking at the entire list is just foolhardy because it's so big, so massive. It's gonna be hard to find what you're looking for. So you need some way to search it. You can search it through the terminal if you want. I promise you can find that same list of counters online. Search it easier that way to find the counters that you're looking for. Remember that by default, it's going to use cycles. How many CPU cycles? So I'm just going to use the default for this very simple execution. And the way that we are going to execute our program, I did something to make this terminal unhappy, didn't I? Is there's a couple ways we can do it. We can do perf stat and then run our, well, should I recompile? Part of me wants to recompile it because right now it's been compiled with the gprof hooks in there, which is going to bloat the execution time. So don't do that on the homework assignment. I don't want to take the time to recompile it though. So I'm just going to run it through perf as is, uh, even though it's not good form. And so here we go. I ran the command stat test and then ran the executable /test gprop. It's got to do its thing. Run. It'll take 26-ish seconds or whatever, 24 seconds. And then once that's done, boom, it's out all of these wonderful stuff. So here's the number of cycles. Here's the number of instructions that were run. Here's the number of branches that were taken. These are all given to us by default. It actually does spit out the seconds elapsed, which is pretty close to what gprof was reporting, right? I would be curious to see if this number changes if I took the gprof flags out of the compile string, right? Does it actually run a little faster if those gprof hooks aren't actually? I would hope so. How much though? Second? 2 seconds? Like, I don't know. That would be a good thing to kind of test out and see what you can see. That would be a good way to answer the first question on the homework assignment, for example. And you can do well, actually, I don't know how you would test perfs overhead. That would be a little trickier since there's no compile flags in there, but you could probably figure out a way. But anyhow, this is kind of the default stuff, which honestly is pretty good, right? These are good general counters that give us they kind of paint a general picture of the code, of how the code is performing. But once again, if you're interested in a specific question, so going back to the homework assignment, right? If I wanted to answer question number 3, for example, that asks directly about the cache, then I'm going to want to start putting some of the cache counters. So there's a way to do that with perf. You'll have to check the documentation. I'm pretty sure it's just a flag, and then you specify the name of the counter that you want. But um, depending on what question you answer, it's going to dictate which counters you want to include and you want to look at. So you'll have to make that choice and use perf accordingly. Trying to think of what else I should show you. Oh yeah, there is another way to run perf that can be useful as well. I should show you that as well. Perf record will actually store the results into a file. So I'll run this program, which probably for the last time. See, run for another 20 seconds. This time the output's going to be stored into a file. Almost there. And I'm going to hit ls to see that, here we go, perf.data is the name of the file that got generated. Once again, if you try to look at that, I don't expect it to be, uh, oh yeah, oh gosh. Yeah, that's not useful to me. We have to use, perf report and then pass in that file. Oh, I think I must have accidentally a thing. What did I accidentally leave out? Probably the name of the command itself. Uh, Here we go. This is what I want to look for. Oh yeah, it's just yeah. I think I overcomplicated it. It's just perf report. My bad. No, it's still not working. See, I screwed up my terminal. Are you having any luck getting this to run? Anybody? Or are you getting the same error as me? Anybody try this? Because I don't know what that error is. I mean, I know it's telling me to set an environment variable, but I don't know what I need to set it to. So, other than that, that error is not very helpful to me. Yeah, that's what I'm expecting. Yes, yes, that's what I'm expecting. And you can actually drill down into those even further. So if you select one of the functions, it should have all the functions listed, yeah? So if you select one of the functions, you can actually drill down more into that function and get more information about that particular function. It is very in-depth, more in-depth than I have time or patience to go through with you all. So look at the documentation. That's your programmers, your experienced programmers. I'm going to point you to the documentation on that one. Sorry I couldn't show it to maybe if I reset my terminal. Let me just restart my terminal and see, because I did something that made it angry. So let me try. Value too large for defined data type. See, that's what I ran into. Okay. That's why I thought you had to do this business. Interesting. I'm just not having good luck with these machines today, which is very. Whoa, what did I do now? I screwed something up on my terminal, y'all, and I don't know what I did. I'm so sorry. Um, I gotta be honest with you. I know the slide said that I like perfect short. Really true. I think I liked you a little bit. I like perf stat better than I like perfect report. Perf stat was perfect. So I would push you in that direction. You can change which counters are shown in perf stat. You can also have perf stat run the program multiple times, correct? Which varies pretty during so much time as well. The downside of having perf stat run the program multiple times is that it does not give you each of the raw data points. It only gives you the aggregates. So if you're trying to do the number crunching and compute error bars and things like that, you need the raw bits. So just kind of keep that in mind as you're working. I think writing a little script or ChatGPT writing a little scripts to run the program a few times might be a better way to go. And I don't have a problem with you using AI for that purpose at all. It sounds like a great use of AI, right? Who likes writing dash? Actually, I kind of like scripts, but I think I might be in the minority. So I'm not going to complain if you all use AI to help make that part a little easier for you. Yeah. So, well, they're all the same. Oh, the boxes are all the same. It's a cluster, so that means every box is the same. Now, you can tweak parameters, so if you request one box with one core and one box with 8 cores, but if you're requesting boxes with the same parameters, and the web interface does make it kind of nice because, again, going back to this one, you can see all of the boxes that you've spun up, and even the ones that are expired, right? That's the one that I ran is that around lunch. So you can see specs and everything. It says it'll be there for 6 more days. So and I also too want to point out that if this session goes away, right? What won't go away are I'm in the wrong place. If I go back to where I was doing my work, right? These files will not go away. So if this session expires after I come back to my new session, that date, those files, right? Those files are my personal user space. They don't get. You're connected to that user space every time. So if you collect a whole bunch of data, like is it, it's not going anywhere. You can leave it on this machine, spin up a new instance tomorrow, and your data is still going to be all the data you collect. Okay. Cool. If the cap is 8 hours, you can't leave it running. I mean, you can leave it running mostly overnight, right? But you got to make sure probably to wake up in time to end your runs before they're forcibly ended for you right in the middle, right? I don't think you're gonna run that problem. I don't really want you to be running for 8 hours straight. That's maybe not good use of time or resources. These programs aren't going to be that. Should not take. They shouldn't even take 26 seconds. That was just an example. It was a little meaty, so we had something to look at besides 0.01 for. So don't worry too much about stuff like that. Any questions for you? Because I don't have anything else to say. I know we still have time left. We still have about 20-ish minutes. I would love it if you would take a look at the homework assignment and ask me questions about the homework assignment if you have questions about the homework assignment, or if you're working with a partner, chat with your partner, make a game plan, decide what questions you want to work on, who's going to work on what, come up with a little game plan. If you want to run an experiment by me, like, hey, I want to answer this question. Would this be a reasonable way to go about it? I would love to chat with you about that. Make sure that your methods are sound and you're not barking up the wrong tree, right? As you're working on the homework. But the rest of the time is for you. So keep practicing, keep working, talk about the homework assignments. Take off if you want to. It's been a long day. I'm not going to complain about that either. But I'm here. Let me know how I can help, okay? I'm going to turn off my recording real quick and then I'll come. I saw a hand back there. I'll be right there.